This is my submission for the Coursera project. So I have done it in Python, and I'll go through the steps and the final results and observation in this video. So as you can see on my screen, I have loaded the Python libraries first. I've used pandas, numpy, matplotlib, and scikit-learn as well as seaborn as well. So this first step is just to load the library. Then I've read the data which was there, the CSV file, ccpp_data.csv. After reading the data, I'm first looking at the first few rows of the data set to understand how the variables look like. Now you can see we have 5 columns: AT, V, AP, RH and PE, and top 5 rows are like this. If I do data.info to understand if there is any null value or not and what is the type of the data set, I can see that it's all float 64 and these are all non-null values, so there is no missing data set. Now this is the details of the project that we have to work on. So the project topic, which is already present in the Coursera project details. Now these columns are defined here. So we have temperature, ambient pressure, relative humidity, exhaust volume and net hourly electrical energy output, which we have to predict. Okay. So first of all, I'll be doing the ED of the data set. So I'm looking at the columns which is present here. Then I'll plot scatter plot of all these 4 different variables with PE. PE is our target variable. So if we look at this scatter plot, so here I am just plotting AT on the x-axis and PE on the y-axis, and if you look at this scatter plot, you can see that there is a very high correlation here between these 2 variables. I mean, they are negatively correlated because as atmospheric temperature increases, the PE decreases. Okay. So, and next, if you see, we'll do the similar kind of plot for V. Okay, V and PE. So here again, it is done in the same way. V is on the x-axis and PE is on the y-axis. Here also, it's kind of negatively correlated, but yeah, the correlation is a bit less. If you look at this chart here and this chart here, you can figure out that yeah, it's a bit more scattered and there are few points which are not falling in this particular line. Now similarly, we can observe the correlation between atmospheric pressure and PE. So if you do that, you can see that they are somewhat correlated, but yeah, the strength decreases. So the first variable is very highly correlated, the second one is less, and this third one seems a lot less. And then similarly, if you do for relative humidity and PE, you can see that this is how it looks like. Here also it's all around the place. Even for the same relative humidity, the PE can vary a lot. Here also same relative humidity, the PE can vary a lot. But yeah, it's somewhat correlated, not that great. Now we can also do this EDA using SNS pair plot. So we'll load this library seaborn, and with pair plot you can observe the same. So if you do this pair plot, you can see we can observe all these details here. So this PE versus AT, PE versus V, PE versus AP, PE versus RH, and we have this distribution of PE. So from here also we can understand that yeah, the peak PE is around 440 and maybe 420 to 460 is the range where most of these PE values fall. And as we go higher than that, 460 and above, the number of instances are decreasing. Okay. Now to build the model, we'll start with the regression model, and to do that, we'll import this library stats model. Here I am creating this X or the the input data set by dropping PE. PE is our target column. So we'll drop that to get this X, and we'll keep P only as Y. So these 2 data frames are created, and then To do the regression, actually you would be adding a constant here. So we'll add a constant here with using this line of code, and then if you look at the data set, this is how the X part of the data set looks like. We have a constant AT, V, AP and RH, and then what we will do is that we'll import this model selection from sklearn model selection. We'll import train test split, and we'll split the data set into two, train and test. So train part would be 80% while the test part would be 20%, and then we'll fit this model sm.ols to this data set. Once we do that, we can take a look at the regression parameters and even the full results. So if you look at the full results, you can see that the adjusted R square is around 93%, which is very high, good value. And all these coefficients, if you look at, as the t values are very high, they are all significant as well. All these are significant, and here from here also you can get some idea that these high t values for AT, it is very high, so it is very much significant. But I mean, we may not like to do that comparison, because again the p is actually very, very less for all these variables. Okay, now the other, so to get the performance of the model in the test data set, we'll import mean squared error, and first of all we will predict. So ypred, we'll use predict function to do that, and with this matrix, if we calculate this mean squared error for on y test and ypred, we'll get a value, and then we'll do square root actually to get root mean square error. So root mean square error for this model on the test data set is 4.63. So this is our observation here. Now we'll import random forest. Here we are keeping these are the hyperparameters, which I have put the value as criteria squared error, max depth to be 3 and minimum sample length leaf is 5. So max depth, actually because we have only 4 variables, so we are not going too deep, and this minimum sample length is again I've kept it at 5. Okay, we can play with this hyperparameters as well to get the best model, but we'll look into that maybe. Maybe for this project I've just stuck with these values to do the comparison. So once the model is trained, actually what we can do is that similarly we can do the prediction on the X test. We'll get ypred 2, and this again, if I calculate the root mean square error on y test and ypred 2, I'm getting 4.87. So this random forest here, we can see that the root mean square error on the test data set is a bit high as compared to OLS. We can also get the feature importance, and here if you look at this AT and V, these two variables are very high, I mean very important for random forest, while the importance of other 3 variables, so constant we should have dropped that as well, but the importance of other 3 variables are kind of negligible here. So the final result and observation is that I'm using this metric root mean square error for comparison of result. OLS and random forest regression models were actually used for comparison, and the results are like this. On the test data set, the RMSE for OLS is 4.638, for random forest is 4.878, and based on these results, I think we can go ahead with the OLS model for this particular data set.